Now, now this is a time to start today's workshop. I'm Naoto Shiraishi, a chair of the first half of today's workshop. The first talk is by Udo Seifert and entitled Thermodynamic Interference, Principles and Application. Please share your slide and start.
Naoto, thank you very much for the introduction. Can you see the slide?
Yeah, I can see your slide.
Oh, yeah, perfect. Thank you. I also would like to thank my colleagues in the OC who asked me to give this talk in this bio and active matter session. So I would like to talk about thermodynamic inference, about a few of its concepts and applications, and the applications will be drawn from the biosystems. So thermodynamic inference means that we use the tools of stochastic thermodynamics to infer properties of a system which are otherwise not accessible. And as a basic paradigm, we assume that on some deeper level, the system we are dealing with lives on discrete mesostates, and I will start by briefly recalling the stochastic thermodynamics for these systems from the bio perspective. And since we cannot observe everything, we always have to, there is some implicit coarse graining when we apply inference. And as we had heard during this meeting already, the coarse graining can happen on different levels. It can happen on the level of states. It can happen on the level of transitions between states. Or we can also look at some coarse grain correlation function, for instance. And then there are various tools for inference, how to use these coarse grain data to learn something about the system. The thermodynamic uncertainty relation is something which has been mentioned several times during the meeting. I will show you that more recently, waiting time distributions have turned into focus as a tool for inference. And at the end, I will tell you about inference from coherent oscillations. Okay, so let me introduce this stochastic thermodynamics on discrete mesostates by using a system which I think would deserve wider distribution. So in my opinion, it's a beautiful experiment from Matthias Reeves' group in Munich some 10 years ago. So they were looking at a small peptide molecule, which they put between these laser tweezers, and then by adjusting or by changing the distance between these laser tweezers, they can apply a kind of pretension on this molecule. And depending on the tension, this molecule is either folded, or it may be only partially folded, or it may be completely unfolded. And the key point is that each of these mesostates comes with a different length. So by monitoring the length of the molecule along such a time trace, they see these individual mesostates. And overall, they could distinguish 6 of these mesostates through such time traces at various constant force. So at any constant force, this is an equilibrium problem. And then they measured probabilities and transition rates. And the nice thing about these systems is that they could demonstrate experimentally that the dynamics between these 6 mesostates is Markovian. So in my opinion, this is one of the cleanest examples which fulfills the paradigms of stochastic thermodynamics. So for such a paradigm, we obviously need that the transitions between the mesostates are slow. There are many microstates, side chains, water molecules contributing to one mesostate, and these microstates have to equilibrate within each mesostate. And then we get trajectories I of t, and the probability to be in a certain state I at time t fulfills this master equation. Now, the rates can, of course, be extracted from such an experiment. So the ratio of the rates is then also given by the ratio of the residence times if you need one long trajectory. And this can be associated with a free energy difference between any 2 mesostates. And if they perform the experiment at a different temperature. They haven't done that yet. I think it should be done, but then you could split that free energy into an internal energy E in an intrinsic entropy S. So I'm emphasizing this here because it proves that you can extract the thermodynamic potentials from experiments, from trajectory data. So there's some criticism sometimes that these are just concepts. No, that's not true. These quantities really exist and you can extract them from data in principle. Okay, so much for discrete mesostates and their potentials. A crucial quantity is entropy production. And as we have heard several times, the cleanest identification of entropy production along a trajectory is the log ratio for the probability of observing this trajectory compared to observing the time-reversed one. And in non-equilibrium steady states, and large part of the talk will about those, there are three representations now for the average entropy production rate. You can either look at the links, you can look at cycles. So here's an example where a 5-state system has two fundamental cycles, or you could look at currents times physical affinities or driving fields. So this AK would be an external force for a molecular motor, or the delta mu of an ATP hydrolysis. And you can, of course, relate all these quantities to each other. And if we were able to observe one of these on these three levels, I mean, at least on one of these three levels, we would have full access to entropy production. However, typically this is not the case. And this leads us to this issue of coarse graining. So very briefly, I think we had this with something like this yesterday. So suppose we have 9 mesostates and they are grouped into 3 coarse grain states. Then, of course, you can still use that definition of entropy production on the coarse grain level. Now, the coarse grain trajectory will be noted by capital I's. And then it's clear that what you infer from such a coarse grain trajectory is a lower bound and on the true entropy production. Now, this log ratio here, on average, is still a complicated quantity for which you would have to get sufficient statistics. So you can simplify and, for instance, just look at the probability to be in one of these coarse grain states, the average transition rate to a state J, and from this, then applying just this Markovian expression, you get a lower bound on this coarse grain entropy, which by itself is a lower bound on the true entropy. Of course, you can do better. You can look at higher statistic transitions from I to J to K. Look at the best Markov models leading to the same statistics. This is something what Skinner and Dunkel recently did, also with nice applications. So I would like to direct you to this paper. You could also look at n-tuples at distinct times. This was one of the suggestions in the early paper by Roldan and Parondo. Now, quite generally, when you have an inequality on entropy production, you can look at this inequality from two perspectives. I mean, this looks somewhat trivial, but I think it's still an important point. So suppose you have an inequality where sigma, the entropy production, is larger than something. Then if you can measure that something, you get an operational lower bound on the entropy production. However, there could also be the situation that this something is a desirable physical property. And then this inequality would tell you the minimal cost of achieving this desirable property. And this is actually, I mean, this perspective is actually what got me into this thermodynamic uncertainty relation. So the original question was really the desirable quantity or desirable object is a precise clock. And the question was how much energy will be needed to run such a clock. And the simplest model, I can be brief here, the simplest model is that we model the steps of the hands of such a watch by an asymmetric random walk. And then after time t, we'll have on average a certain number of steps n, but this will come with a variance. And from those, we get an uncertainty. Now, since the whole thing has to be thermodynamically consistent, there is a cost associated with breaking the time reversal symmetry of equilibrium. So that cost is given by the rates in this form. And the rates are associated with the driving affinity. This is now the simple affinity of such an asymmetric random walk. And as you know, when you combine these quantities, you find that the product between cost and uncertainty is given in this particular case by this hyperbolic function, which often pops up in this field, and that is bounded by 2 kBt. Now, it was then later proven by the MIT group that this relation holds for any Markov network. So I still like this number. So when you have a precision of 1%, you have to pay at least 20,000 kBt. And the key point is that it holds for any current in such a stationary Markov process. So you could say it holds for any clock, but as we have learned from Patrick 2 days ago, quite surprisingly, it is violated as soon as you allow for inertia. Okay, so what can you do now with this uncertainty relation for inference? This is still my favorite example because it's an application which deals with the real world and it uses just experimental data. So more than 20 years ago, in Bloch's group, there were measured the motion of a kinesin molecule which runs along a microtubule driven by ATP hydrolysis, and it runs against a constant force which is implemented by this laser tweezer, or this speed in this laser tweezer. So what they measured at the time was the velocity of the motor, the diffusion constant, i.e. the dispersion of this motion, and they combined this in this ratio, which is called randomness parameter. And the data then looked like this. I mean, here is the randomness as a function of the ATP concentration for various loads here in the piconewton range. Or you could look at the randomness as a function of the external load or force for a fixed ATP concentration. So these are typical data which you get from the experimental lab. And the question is, what can you do with this data? And essentially, there are two approaches. You can now try to build a model of this molecular motor that will contain parameter. And then you can tune the parameter for a while till you can reproduce such experimental data. Now, the thermodynamic uncertainty relation allows us a different approach. It allows us a model-free approach to get information on this motor. And it will be information about the efficiency. So what is the efficiency of a molecular motor? Or of any machine, actually, it's the ratio between the output and the input. Now, the output of this molecular motor, if it runs against an external force, is force times velocity. The input is not known experimentally because you cannot see how many molecules of ATP vanish if such a molecular motor runs along the track. However, we do know that the difference between input and output is what is lost. That's the entropy production. So we can replace the input by the output plus the entropy production. And for the entropy production, we have the uncertainty relation. So we plug that in, and then we get this inequality here. And this, the right-hand side bounds is an upper bound on the thermodynamic efficiency. And the key point is that here only experimentally measured or known quantities enter. So if we take the previous data, and we overlay this, this curve here, we get this kind of diagram. So let me take this data point here for an explanation. So this data point is the measured randomness, i.e. the measured ratio between velocity and diffusion at 2 piconewton load. And our curve here, the orange curve, is the 45% curve. So the tour tells us that under these experimental conditions, this very motor is at most 45% efficient in transforming chemical energy into mechanical work. And if we take, for instance, that data point, we have the same statement, but now we are at 75%. And the key point is that this statement or this result is completely independent of any assumption about how this motor works. I mean, we're just assuming it's in steady state, which it obviously is. And we're assuming that at some very deep level, we don't need to know on which level, but at some deep level, we have this Markovian dynamics. Okay, so this is still my favorite example for explaining the power of the tour. Let me now show you a further result of inference when we have more information. This is now a version of the tour which is more detailed. So the left-hand side involves entropy production, diffusion coefficient, mean current, and typically that is larger than 2. But on the right-hand side, you see now a function which reminds you on what we did for the asymmetric random walk. But this holds now very generally in multicyclic networks. And A over n star is the minimum of affinity per cycle divided by the number of this cycle, the minimum over all cycles in a multicyclic network. And this can be used for inference of topological aspects of biochemical reaction networks. And let me show you a simple example. Michaelis-Menten kinetics is that you have an enzyme which binds a substrate, which transforms it into this product and then releases the product. Now, we know that such a transformation will be, for instance, be powered by ATP, and let's assume that we know the delta mu of the ATP hydrolysis because we know the concentrations. Now, this bound here, this refined uncertainty relation leads to a bound on the Fano factor, where little n is the number of products generated in a cycle, capital N is the number of states. So this bound translates into a bound on this Fano factor. And let me show you just two alternatives. So suppose we know that we know the delta mu, then if the simple Michaelis-Menten scheme applies to this enzyme for which we can measure the diffusion and the dispersion and the mean current, then this Fano factor has to be above this line indicated by the 3 here. If we measure Fano factor less than that, it cannot be realized by the simple Michaelis-Menten scheme. However, in this blue strip, it could be realized by a more complex scheme where the enzyme can bind 2 substrates, transform each of them into a product. And here, the crucial cycle is this cycle here, which has 5 states, but there is only 1 product generated in this big cycle, which leads to a smaller quantity here. I mean, this is not a terribly large range where we can discriminate between these 2 schemes, but that's not my point. My point is that using this tool and some additional information, for instance, that each cycle involves a delta mu or an integer number of delta mu's, which you know, you can infer statements or you can infer certain properties of a reaction network. Let me come now to a second variant of the tour, which has to do with the fact that we may also look at time-dependently driven systems using the tour. So this is work with Timur Koyuk, where we derived a quite general relation, which I want to explain. So suppose that in such a network, the rates are time-dependent through an externally imposed protocol lambda of t. And we assume that there is an experimental knob which speeds up or slows down that protocol. And the system is driven for a total time calligraphic t. Now, as observable, in this case, we don't have to use a current. We can, for instance, use the total time spent in any of these states, which is capital AI. And that will depend on the total time. Now, the generalization of the tour involves the mean of this quantity, the dispersion of this quantity, and here an additional expression which looks at how does the mean change when we change the speed of the driving or when we change the observation time. And then the left-hand side is a lower bound on the average entropy production through this time t. And you can do the same thing, not for the total time spent in a state, but you could also look just at the observable, the state at the final time. How does that change when you speed up the protocol? Okay, so let me now show an application where I come back to this Kalmodulin experiment. So in this experiment, as I said, we know basically everything from the experimental data. So we are now assuming that we are looking not at a constant force applied to the molecule, but rather that unfolding under a force ramp where V times T is the speed, V is the speed with which the force changes. And as observable, let's just take the characteristic function of one of these mesostates here, state F12, or we could take the observable where we look at the total time spent in the unfolded state. Here in this diagram, you see the data. The data give the so-called quality factor, which is the ratio between this lower bound and the true entropy production in the process. And we know the true entropy production because we know all the rates in the system. And you see that now, depending on the observable, the red one and the blue one are the two I explained, we get something like, and also depending on the speed with which you pull, you get something between 20 and 80% of the total entropy production. And you can, there's also a variant of the uncertainty relation where you can use the current, this is the green curve, current variable. So the bottom line is, again, even for these time-dependent situations, you get a reasonable estimate on the entropy production, a reasonable lower bound, by just looking at such observables like mean times or final residence state. Again, it's a model-free estimate, and in this particular case, we can assess its quality because we know the underlying, all of the underlying rates. Okay, now let me come to a, I think, even more exciting recent development. So basically, the idea now is that we're looking at waiting time distributions between transitions, and this is something which started perhaps with this paper, and there are a couple of contributions. I will be explaining what we did recently. So for a start, let's assume originally we have this four-state network, but we were able only to look at the transitions between state 2 and 3 and state 3 and 2. So this would be a fine-grained trajectory on the mesostates, but we are able only to observe the transitions between 2 and 3 and 3 and 2. But now we are looking at the waiting time between two consecutive transitions which we can observe. For instance, the waiting time distribution for a transition from 2 to 3 and a consecutive one, 2 to 3, which I'll call psi plus plus. There's also a psi minus minus and there psi plus minus, which we don't need. And as the crucial observable, we're looking at the log ratio of the distribution between two plus transitions divided by the time-dependent distribution for two minus transitions. And here you see specific data. Now I will explain in 3 steps how we can use such information. So suppose we had originally a unicyclic network. So suppose this transition between 1 and 3 was absent, and this would just be a unicycle with 4 states. But we're able only to observe the transitions here. Then it turns out that this A of t becomes time independent and is actually given by the affinity of the cycle. So in this case, you get the affinity of the cycle exactly. Of course, you also have the current if you observe here one link. So you get the full entropy production by just looking at one link. And I want to stress that this is better than if you apply the Tour in such a situation. If you apply the Tour in a unicycle just to one link, you get not the full entropy production in general. So this already indicates that these waiting time distributions contain more information on using essentially the same data, because if you want to apply the tour, you also have to monitor this transition. Okay, now of course, the more interesting case is that we have a multicyclic system, a multicyclic network, and I will still stick to the situation where we can observe only one link in this more complex network. And in this case, this ratio of waiting time distribution between two 7171 transitions or two 1717 transitions, that becomes now time dependent. And these are real, a real curve with real rates. Okay, now what can you infer from such a curve? Well, several things. First of all, if you look at the limit of this quantity for time going to 0, you get the affinity of the shortest cycle to which this link contributes exactly. So in this particular case, the shortest cycle is the 3 cycle 172, and you get its affinity exactly by just looking at the t to 0 limit of this ratio. Now, as you can see, this ratio has minima and maxima, which may be either t equal to 0 or infinity, or you may have intermediate ones. Now, what we can prove is that the maximum of this A of t curve is a lower bound on the maximal cycle affinity to which this link contributes. And likewise, the minimum is an upper bound, and we allow here, of course, for negative values on the lowest affinity to which this cycle contributes. Now, in order to assess the quality of such a bound, we looked here at the quality factor for about 2 million networks, sampled different rates. And you see again, this is a cloud which typically ranges between 20 and 80 or 90% for different situations. So such curves indeed contain information about the affinity of the shortest cycles, and you get reasonable bounds. And you can even infer topological aspects, which I don't have time to enter now. Now let's look at the situation where you have a multicyclic system, but you can observe several links. So let's say you can observe these 4 links, and then you can look at the rate with which an I transition happens. So these are 4 choices here. And you can look at the waiting time distribution of a consecutive transition J after I, which is this psi ij. And then again, looking at the log ratio of such a quantity, weighting it with the corresponding weight, integrating over time, you get an estimator on total entropy production. And you even get a criterion whether or not you get the full entropy production. Turns out that if all of these ratios are time independent, then you basically get the full entropy production, because that means that you have observed one link of each of the fundamental cycles. Okay, so much in a nutshell what you can get from these waiting time distributions, and I think that carries lots of promise for inference. Okay, let me now come to my final topic, which is inference from coherent oscillations, or acquiring this dual perspective on the problem. It's also about the cost of having coherent oscillations. You all know that in biophysical, biochemical system, oscillations can spontaneously develop even under steady state conditions. So we have to distinguish here steady state conditions, i.e. there is a constant external driving by providing a constant excess of ATP, for instance. And then if you look at some quantity, like here, the expression level concentration of a certain protein, you get these kind of oscillations. So this is the circadian clock system reconstructed from the cyanobacterium. It's what is called the Chi system. There is a constant input. You can do it in the test tube, and then you get these oscillations. And of course, I mean, the fact that you get oscillations, that has been known for a long time. And you do not only want oscillations, you want that these oscillations to keep phase. So you want these oscillations to be coherent over different realizations. And the question is, again, is there a relation between the coherence of these correlations, of these oscillations, sorry, and the energetic cost of the process which generates the oscillations? And we're looking at, again, at the simplest kind of model. So we take this asymmetric random walk, in which case you can calculate everything. And from this, we conjecture a universal relation. So here are data. So suppose you have not 3 states, but you have 100 states, homogeneous K plus K minus rates, an affinity of 200. And then this gives you a correlation function. This is the correlation function for being in state 1 at time t, given you start at time 0 in state 1.
You've spent 30 minutes, so please summarize in a short.
Yeah, I will. Yes, I will come to the end. There are just 2 more slides. So in this case, if you look at the data, you see there's roughly about 4 coherent oscillations, and then the amplitude has decayed to 1 over e. So the general expression, of course, for such a correlation function is a sum over complex exponentials, and dominated by the second eigenvalue, you find that the coherence is lost, or the ratio for the number of coherent oscillation is given by, sorry, the ratio between the imaginary part and the real part determines the number of coherent oscillations. That's how it should be, right? And in this asymmetric random walk case, you can calculate it easily. A is the affinity, n is the number of states. And then you can also calculate the free energy cost per coherent oscillation, which I call delta S here. Again, a hyperbolic function, which is larger than 4 pi squared times calligraphic n being the number of coherent oscillations. And based on a lot of numerics on limiting cases, we conjecture that this is, again, is a universal relation. So whatever you do, if you want to have n coherent oscillations, you have to pay at least this 4 pi squared n for each of them. So the more coherence you have, the more you have to pay for a single oscillation. And we have tested this using a kind of real-world example. This is a model for this Chi-C, Chi-A clock from Ten Volders and co-workers some 15 years ago. So it's based on hexamers of Chi-C, which are phosphorylated, dephosphorylated. They compete for the Ka molecule. I have to speed that explanation up. And this shows nicely oscillations, and we've modeled this. And here are the data. So the dotted line is this universal bound. And these are the real data for such a realistic network as a function of the delta mu driving the process. And you see the data are about a factor 2 or 3 of the bound. And that should not be too surprising, because you do not expect such a network to work like an asymmetric random walk. Okay, so let me briefly get to the acknowledgement. So the work on the uncertainty relation is with Andre Barato, Patrick, Timur Koyuk is currently a PhD student finishing in my group. Waiting time distribution is new work by 2 PhD students, Benjamin Ertel and Jan van der Meer in my group. And coherent oscillations started with Andre some time ago, and Lukas Oberreiter is about finishing his PhD. So I hope I've shown you that this inference using stochastic thermodynamic tools is an exciting area, and I would expect that at the next meeting we'll have more to report. Thank you very much.